Welcome, everyone, and thank you for joining today's webinar. Ever wondered why two identical samples can deliver wildly different XRF readings? Did you know that anything between 50 up to 70% of analytical errors in XRF stem from what happens before your sample enters the spectrometer? If you've ever wrestled with inconsistent results and lost hours with troubleshooting your prep method, this session is for you. Today's webinar, Important Considerations in the Analysis of Fused Beads, will explore how to improve the accuracy and reliability of your XRF data through better sample preparation and fusion techniques. Our host today is Frederick Davids, Global Sales Equipment Manager at XRF Scientific. Frederick brings over 25 years of expertise in sample preparation techniques, including XRF, ICP, and thermogravimetric analysis. Joining Frederick, I'd like to welcome our special guest, Pol de Pape, a consultant specializing in XRF analysis and sample preparation with more than 35 years of industrial and commercial experience. We, of course, encourage you to ask questions anytime using the Zoom Q&A button, and we'll answer them after the presentation or follow up with an email. XRF Scientific is a global leader in the field of sample preparation for XRF and other analytical techniques. We have a global footprint with manufacturing, sales, and support in Perth, Melbourne, Europe, and Canada, as well as a distribution network spanning the Americas, Africa, the Middle East, and Asia. XRF Scientific supplies world-class fusion equipment, platinumware, chemicals, and consumables to laboratories across numerous industries. With that, let's get started and turn unpredictable readings into rock-solid data. Over to you, Paul.
Hey, thank you very much for the introduction, Jackie. Indeed, let's talk today about the fused bead sample preparation method. And Frederick, who's sitting here at my side, will show you the sample preparation equipment and chemicals that XRF Scientific has available.
Yeah.
So let's kick off here with a short introduction about what is now elemental analysis about? What is the all-over objective? So what do we want to reach? Well, first of all, I think we want to reach a high, accurate, and precise results of our sample. In order to do or to have so, we have to take into account some potential sources of error. So these are processes that need to be controlled. And there's quite a few sources of errors that we will see. And today we pick out just one, and this will be the fused bead sample preparation methods. So as Jackie already mentioned, the sample taking and especially the sample preparation is really responsible for a big part of our analytical error. And it can go up to 80 to 90%. Of course, depending on how good we are, this error may be less or maybe more. The error will also depend on the quality of the standards that we are using, the quality of the calibration that we are setting up. Are we using the right correction models? Also the calibration maintenance, of course. Yeah, we have to keep our instruments reproducible, and calibration maintenance is one part of this. So just to come back shortly to accuracy and precision. So the accuracy is really the proximity of the measurement result to the true value, and the precision is the repeatability of this measurement, or also really we can translate it into the lower limit of detection, as we will see also later in the presentation. But now just briefly about XRF. So X-ray fluorescence is a non-destructive spectroscopic technique that is dedicated to the analysis of the elemental composition of a large variation of samples. So these samples can be liquids, can be solids, can be powders, can be anything, can be small pieces, large pieces. In big lines, we can distinguish between two different XRF techniques. That's energy dispersive and wavelength dispersive. In energy dispersive, the spectrometer has an X-ray tube and a detector, a high resolution detector that will separate energies. And in wavelength dispersive, we will separate the different energies. In that case, we will really speak about wavelengths by means of crystals. It is important, of course, that you choose an appropriate spectrometer, and the choice should be made depending on the analytical tasks. We know price is always an issue, but the analytical task should really be the main thing we have to look at to choose our spectrometer. Anyway, whatever spectrometer you have in your laboratory, or which you may have in the future in your laboratory, it is always very important to have a well-prepared specimen into your spectrometer to obtain good results. Because we say garbage in, garbage out. Let's have a short look now at how XRF works. What is the principle for those amongst you who are new with this topic? So the principle is like this. We have a sample that contains a huge amount of atoms, and I represent just one atom here, which is in our specimen. So by means of an X-ray tube, we will shoot primary X-ray photons onto our specimen, and the electrons, the inner electrons, may be excited, forming a photoelectron. Now this atom is going to try to stabilize itself again, and external electrons will drop into this vacancy, and the difference in energy between the inner electron and the outer electron is really what we are going to analyze as fluorescent X-ray. Let it be energy or wavelengths. The sample preparation process is very important. So first of all, we start with collecting a representative bulk sample. So the bulk, this can be many tons of material, it can be ore, it can be oil, whatever your bulk sample is, we speak in general about tons. And from these tons of material, we want to prepare a representative sample for the laboratory. A sample that the laboratory people can use to make their final specimen that will be analyzed. So in our case now, we will talk about fused beads preparation. So in general, we have like a specimen of 0.1 to 10 grams, but for fused beads, in general, we have less than 1 gram of sample. So 1 gram representing the tons of material. Remember this. So tools are also being provided by XRF Scientific to make sure that you do have a decent laboratory sample available. And I show just a couple of the tools here. We can see here a jaw crusher, we can see here a fusion device, we can see here an automatic press. All tools that can help you in the laboratory to provide your specimens that go into the spectrometer. Now, to decide what is now the way I'm going to prepare my specimen. It will depend on a couple of parameters, which are the physical form of it, the sample size, the quantity of sample we have, and how much time do I have to prepare the sample, which is in general related also to the cost. And the reproducibility of the preparation method is, of course, also very important. And at the end, the required analytical accuracy and precision, also detection limits, will depend on the way or the way we will prepare our specimen. Because at the end, no preparation, for example, is very easy. We don't invest much time, the cost is low, but the results may be of lower quality. And the further we go to the right, the better or the more efforts we have to have, the higher the cost is, but also the results quality goes up. And fused beads we put at the far right side, so there we can expect the best results quality. Now, what is more specifically the aim of the sample preparation for XRF analysis? Now, first of all, the sample, it must fit into our spectrometer holder, into our sample holder. The sample must be as homogeneous as possible. It must have ideally a very flat surface without any irregularities, because these can lead to bad results. It should also be ideally relevant to the X-rays that penetrate the sample infinitely thick. And of course, it must be stable under X-ray radiation in vacuum, helium, or whatever other gas you may use. So we don't want the sample, of course, to drop into our spectrometer. That's bad. And it is always good that the sample that we prepare can be reused over a longer period of time. Now, what are important parameters when we talk about the fused beads sample preparation? Well, first of all, we need decent devices. You can see here the XR Fuse 6, which is a 6-position fused bead machine. So you can prepare simultaneously 6 samples. And as mentioned before, we want to have these samples very homogeneous and with a flat surface. We want to eliminate grain size effects and mineralogical effects. We want also to reduce matrix effects and detector saturation. Sometimes you have samples like an iron ore, a copper ore that may have a very high concentration of the respective elements that saturate your detector. By diluting it, making fused beads, we can reduce this. And also we want to increase our analytical accuracy and precision. It is also very fit for small sample quantities. If you have just like a couple of tenths of a gram of a sample, you can still make a decent fused bead out of that. And a big advantage is also that you can make your own standards by making your own chemical mixtures. But we can always explain you more about this if you have a specific question to that. I'll pick out just two of the effects that take place, just to explain you how we can resolve them. So in this example, we just assume that we have two particles, that's silicon oxide and aluminum oxide. And now the grain size is very important, because if you have, for example, a larger grain size, we have a certain distribution of those two particles, and the intensity of the particles is really a function of the number of particles within those analyzed volumes. Now, if I start grinding the samples to a smaller grain size, the distribution may be different, and therefore also the intensities may be different. Although we do have the same concentration in both samples, grinding the sample down to a smaller particle may drastically influence the measured intensities. The second effect is the mineralogical effect. Now, as an example, we have here the cement clinker, which does have, if you look closely for calcium, 5 different phases. So the calcium really comes from 5 different phases. And therefore also the intensity is from those 5 different phases. So the compounds are not necessarily present as pure oxides, but as different kinds of phases, also called structures, which do have, again, an influence on our intensities. And we can see here an example. A cement clinker, in this case, we're just analyzing aluminium. And we can see here on the left-hand side a calibration curve for aluminium based on the pressed pellet method, which, by the way, we will discuss in the month of November also. And on the right-hand side, we can see exactly the same calibration standards, but now prepared as fused bead. And you can see that the linearity, the accuracy of our fused bead method is much better than for the pressed pellet method. There is a number of additives that can be used, that shall be used, and that have to be used also for making our fused beads, depending a bit on the sample we are looking at. But what we will always use for whatever the sample is the so-called fluxes. And these are meant to digest the sample. And the choice of the flux will depend strongly on the sample composition. The fluxes are in general high purity and pre-fused granulated borates of lithium and sodium. The next important additive is the oxidants. So these oxidants are there to pre-oxidize especially metallic, sulfuric, and phosphoric samples. And in order to do so, we are using nitrates of lithium, sodium, potassium, and strontium, depending on what are the elements that you want to analyze. So lithium nitrate is one that is normally used because lithium in general, well, not in general, we can simply not analyze it with XRF. So that's why this one is a very interesting one. Of course, if you don't want to analyze sodium or potassium, you can also use those nitrates. They have a different decomposition temperature. We will see later in Frederick's part. Non-wetting agents, also important because these reduce the viscosity of the sample and it prevents sticking to the platinum ware. So if you wouldn't use those non-wetting agents, your platinum ware would be completely dirty. It makes it more difficult to clean it. And in general, that's iodides or bromides of aluminium, lithium, and ammonium. Internal stands may also be used. And these internal standards can be used to correct for eventual intensity changes of analytes due to the finite thickness of the sample, or maybe also due of spectral interferences. And important is that we use chemicals that show a similar behavior as the element that we want to analyze. So if we want to analyze, for example, molybdenum, then niobium is an ideal element to use as an internal standard for molybdenum. Fluidizers is the last additive we speak about, and fluidizers are used to increase the melting efficiency to improve the fluidity, so to cast it easier also. So lithium fluoride, boron oxide, sodium, or lithium carbonate are therefore used. And the fluxes we will later on look at in more detail with Frederik. You will see there are some really specials that XRF Scientific can offer you. But what is now the all-over principle of fused bead preparation? Well, it's a chemical reaction by which we are going to transfer metal-containing phases. Metals in that case is the elements that we do want to analyze, and we will convert them into glass-like borates by means of those fluxes. And of course, we will also use a high-temperature fusion device. And well, actually today we still have it up to 1,200 degrees, but actually today we already have systems available up to 1,300 degrees. But it is important that we obtain a non-crystalline solid glass disc. And this is more or less the reaction that takes place. So lithium tetraborate will be divided into two different chemicals, and those chemicals will react with our metal-containing phases. So the elements really that we do want to analyze. And at the end, we will get a complex borate that has the same form for all the phases. So do you remember the clinker where we had 5 different calcium phases? Well, when we are using the fused bead method, all the calcium phases will have the same borate complex. So, as mentioned, fusion is a chemical reaction, but it is now, of course, important that we have a very homogeneous sample. And therefore, what we already can do is we can mix the flux with our sample already. Okay, we have special cases where we need some pre-oxidation, so we cannot do this, but in general, we can mix oxidic samples already with our flux to have this pre-mixed to make sure that the reaction is way better and faster. And when we see we have a very homogeneous content of our platinum crucible, we will cast it into the glass disc that has this nice boron oxide glass structure. There is a number of tools that we can use to make our life a bit easier. More details will follow later on, but it is important in order to have a good fusion to have small sample particle size, to have an adequate flux for the type of sample that we analyze, that we have additives to choose out of, that we have the right sample to flux dilution ratio, that we have appropriate fusion temperature and time, that we homogenize the sample during the fusion, and also that we make sure that our casting disc has an appropriate temperature to cast the content of the platinum crucible. More details will follow in the second part of the presentation. Here we can see just a typical fusion program. So the fusion devices of XRF Scientific can be calibrated, they can be defined just to your wishes. And of course, XRF Scientific does have the knowledge, so they already have some pre-defined programs. But in general, we have like 3 main steps. It's the pre-treatment, which can be consisting of the oxidation and the decomposition part. Then we have the fusion, which is the actual melting and the mixing of our sample with the flux and the other additives. And then we have the cooling phase. The sample to flux ratio will depend strongly on the dissolving capacity of the sample in the flux. And generally, we are looking at 1:4 to 1:10 dilution ratio. Of course, measured intensities are proportional to the dilution ratio. So what does this mean? When we do have a high dilution, for example, 1:10, then the matrix effects that may be present in the sample are strongly reduced. But on the other hand side, the detection limits may be a bit higher because we have lesser intensities. And when we have a low dilution ratio, for example, 1 to 4, the matrix effects may be stronger and you may have to use the software of the spectrometer to resolve that. But we may have better detection limits. So it's always a compromise. So detection limits is a question that very often comes. So therefore, I just give here 1 minute attention to lower detection of limit. Lower limit of detection, sorry. So the lower limit of detection is really defined by the peak to background ratio, but also by the measurement time. So we can see when we have a high peak and a low background, we have a very good lower limit of detection. And now this lower limit of detection can also be steered by the measurement time. If I'm going to measure here like a factor 4 more, my lower limit of detection, we can see it's a square root function, will be 2 times better. So lower limit of detection depends on, let's say, the sensitivity of the elements in the sample and the measurement time. What we can see here now is 2 different sample preparations, a 1 to 6 and a 1 to 10 dilution for 4 different elements. Iron being a heavier element and magnesium being the lightest element. So we can see when we use a dilution ratio of 1 to 10 that we have less intensity than when we are using a 1 to 6 dilution ratio. And this is true for all the elements. So we must be aware when we use a higher dilution, we have lower intensities, and therefore for some elements we may not be able to analyze them anymore because the concentrations become too low. Now, if we do have just a little bit of sample, we have a solution. XRF Scientific can offer you different sizes of casting dishes. So we can see here one of 10 millimeter, and we can also see the larger one, which is probably 40 millimeter, and we can go up to 40 millimeter dishes, so from 10 to 40 millimeter, and things and size which are in between. So this is a nice choice that you have. Well, we will see now that depending on the size that we are using, or maybe the sample quantity that we use, we will have also a strong influence on our intensities. And we will have a look on the next slide now to mask sizes in the spectrometer between 8 and 32 millimeter. So we can see here now different elements: iron, calcium, silicon, magnesium again, so heavier elements and lighter elements. And we can see that for the 32 millimeters down to the 8 millimeter, we can see peaks for iron very clearly, also for calcium and silicium. Magnesium is already getting a bit more difficult. So here we can really see with an 8 millimeter mask, we have basically lost our peak. So again, we can see an influence on the size of our sample. Now, there are a few limitations, of course, also nothing is perfect. Still, there are solutions. So the fused bead method is really ideal for already oxidic samples. But what we have to bear in mind that when there are volatile elements like sulfur, arsenic in our sample, we may lose them. Yeah, the same for carbonates, of course. Yeah, people working with cement will know this. Yeah? The cement furnace, we will lose carbonates by high temperatures. The same happens in fused beads. And also the dilution of the original sample makes the detection limits less good. This is, for example, important in geological samples. And we cannot analyze elements lower than fluorine, or equal to or lower than fluorine. Also bear in mind that precious metals like gold, silver may react or will react with platinum. So it's not possible to make fused beads and analyzing those elements. And as mentioned before, metallic sulfuric sample or only partially oxidic samples will need some pre-oxidation. So we need to take special care because we may ruin our platinum where we may have very bad quality fused beads, you know, so we have to be very, very careful. But always remember, XRF Scientific can give you indications when you have special sample, you're not sure, how do I have to prepare, please contact us, we can help you. So we see some ideal samples here on the left-hand side. And of course, we also have to show what can go wrong. So we can see diffuse samples, non-transparent samples, samples that still contain some particles, samples that crack, and this all has a reason. So we will look at this also in the second part. But the question is also, well, what do we do with loss on ignition or maybe gain on ignition in XRF analysis related to fused beads, related to pressed pellets, which will, I repeat, in November be another topic we will talk about. Yeah. So when we talk about the pressed pellet sample, we know that the LOE and all the other components are still in the sample. They make part of it. In the case of a fused bead analysis, so we will lose these volatiles. The loss on ignition will be lost when we heat the sample up. So we must take this into account in our calculations, or maybe introduce in the software of the spectrometer. Now, this was, let's say, the theoretical part. Now, Frederick is going to take over from here and give you some more information about XRF Scientific's equipment and chemicals.
Yeah, thank you, Paul, for all this valuable information, being very, very instructive. So yes, when we speak about the equipment and chemicals needed to do a proper fusion glass beads, I will just list all the items, materials needed. So of course, first you need a fusion machine. You need to have the fusion labware, crucibles and molds. The boric flux and additives, like explained, the analytical balance, an automatic weighing system if we have a lot of sample to D per day, or for health reason, spatula, of course, and span, mixing tools to mix the flux and the sample before the fusion. That's really important to start already with an homogeneous mixture to save time and avoid there is materials agglomerate in the bottom of the crucible. Micropipette is when you are using the non-wetting agent as a liquid form. You cannot just add drops with a dropper. You need to have something to calculate or measure perfectly the quantity you have. And then you can have some tools to, I would say, improve the process, like a glass disc remover to remove the beads at the end, and also ultrasonic cleaning system for cleaning the platinum crucibles and molds. So first, the fusion machine, and if we speak about what we have available at the XRF Scientific, so you have two different type of device of heating system. So you have the electrical fusion system called XRF Fuse at XRF Scientific, and we have different capacity machine. And it allows me to present you our far new fusion machine with 1 and 2 position, the XRF Fuse 1 and 2, where we have a lot of new improvements. For example, the maximum heating temperature can now be set at 1,300 degrees, but also we have new features for increase the cooling process, and not only the molds but also the crucibles, and all made to allow the operator to be in a safe environment and condition, and of course increase the throughput. And of course we have a 6-position machine, so if you do I would say 100 speeds per day, that's what you need, and more, of course. And then after we have the gas fusion machine, and for that we have, I would say, so the Phoenix is our system, and we have, I will say, 2 type of machine. So we have first the Phoenix Go, available in 1 and 4 position, and when we say go, it means that we use gas only, so only combustible gas. So the burners are doped, are boosted with fans to push air, oxygen in the flame, and be able to reach 1,200 degrees. And then after we have the, I would say, our standardized machine. We started more than 30 years ago using propane, oxygen, and air, and this machine is still working in a lot of labs. It's very rugged, strong. It's made for lasting, clearly. The platinum Labware is also really important, and for the XRF fusion, we are using the platinum gold alloy. This is the reason first is because it's far more strange compared to the pure platinum. We have an excellent chemical resistance. Of course, if the elements are metallics, you need to oxide it, but nevertheless, you have good resistance. And also the fact we have 5% gold give a non-welding property to this alloy, and of course it's very good to release easily the beads from the molds. Also, what is really important is the mold thickness. So we recommend to have a mold thickness of minimum 1.2 millimeter. And why? Because we want to keep the flatness of the mold as longer as possible. And the surface of the mold, this is the analytical surface. And of course, if this is not perfectly in perfect condition, so if it is deformed, if it is scratched, then of course you decrease your analytical result and mostly the reliability. So there is clearly a change in the results you get with a deformed mold. So it's really important that you take care of all your platinum Labware. Of course, for the crucible, it's mainly to avoid product is sticking and it takes a long time to clean and etc. and you have cross contamination. But like I told you, to protect the analytical surface of the mold. And for example, you can see some bad behavior. For example, putting all the molds in contact of the analytical surface is definitely not a good idea. And if I take, for example, the case of iron ore and the analysis of iron, we can see that if we have deformed molds, so we obtain a deformed bead, and the analytical error obtained can be up to 1% relative.
Yeah.
So it's very big. It's very important.
And the reason here is that if we have like a curved sample, the sample is close to the X-ray tube, and of course we get a higher concentration because we have more excitation of the elements.
Exactly. The distance is not the same with the detector. Okay. Yeah. So the fluxes we already spoke about. The fluxes, we have two types, the granular powder and the microbead structure, and different purities. So the purities are really important, of course, because it's important for you to know what impurities you have in the flux, because of course you will see it after in the analysis. And of course, it's also multiplied by the dilution factor. So if you have 10 ppm iron, you will see 100 ppm if you dilute 10 times. So it's really important to know. The flux are often made of 100% lithium tetraborate up to 100% lithium metaborate and a mix of both. And you can have the additives. So you can have a flux with a non-welding agent, lithium bromide, lithium iodide, or you can have it with oxidizer, or you can even have it with oxidizer and non-welding agent. So it's very useful because you don't need to weigh separately the different chemicals. And also you have flux with the internal standard, like you spoke about. And for example, the thulium is really often used in the nickel mining world, especially for analyzing the nickel, because you have very good results for that. The flux, the use of the flux are characterized by their acidic or alkali properties, character. And so, for example, the most lithium metaborate is the most alkali flux, and the lithium tetraborate is the most acidic. But also, you will use the flux in function of their fusion melting temperature, because you want to keep as much as possible the volatiles in the flux, in the sample, sorry. And so, of course, the lower temperature, the better it is. And of course, you can see that all type of flux mixture is more adapted to specific materials. And of course, we can help to make a good choice according to the temperature and according to the type of materials you use. The flux purity, like I told you, it's really important because it will determine what I will say impurities you will have in it, and what you need to be aware. Of course, if you do pure analysis, for example, you have the sand producer who want to detect the quantity of iron, and of course, for them, 70 ppm is really important. And like explained, you need to first make, for example, a batch of your flux to be at least be aware of what you have in the flux. So automatic weighing, of course, it's most used when you have a lot of samples to do per day to, I would say, to let a machine doing a boring task for you. And we have for that the XRF weight carousel with 30 position, 30 vials, but also for health reasons. And as you know, the flux are not the best chemicals for the operator, and so it's good to have a machine that avoid the chemist is too much in contact with the flux. So just put the crucibles and the machine do the rest. So it allows you to keep away. And of course, you have a better repeatability because you avoid human errors in the weighing process. The additives. So for the non-weighing agent, we have a different type of non-weighing agent, and most are halogenides. The most used are the lithium bromide and the lithium iodide. And if you use it, you use the non-weighing agent with an automatic injection system, you will use the ammonium iodide, who is available in small tablets. You can inject automatically in the crucibles during the fusion cycle. And the advantage of that is the tablets are always distributed in the crucible at the same time during the fusion cycle. So if you have a fusion cycle with oxidation and the next one without oxidation, you have always the ammonium iodide 1 minute before the pouring. So it's always same quantity in the bead.
In the same time.
Yeah, exactly. And I will say the lithium iodide and the lithium bromide are the most used, but lithium bromide, I will say, is less volatile and remain more time in the bead. So you have a better effect. If you use lithium iodide, you need to put more lithium iodide in the flux because most of the iodide disappear, and so the effect disappears. If you have long fusion time, iodide is not the best, clearly. And so you need to find the ideal quantity. And of course, if you put too much, you can have a moon effect. And if you put no non-weighing agent or just a little, then you can have the beads cracking, or you can have the material sticking in the bottom of the crucible. I would say it's really there is an interference effect by adding iodide or bromide, and you need to be aware of that. But of course, if you use the same flux for the calibration and the flux for your routine analysis, the effect is depicted. But really using non-weighing agent help for the day-to-day work, because it's more easy to clean the crucible, to release the beads. So we definitely recommend to use non-weighing agent. The oxidizer, like Paul already explained it, it's really important for many reasons. First, because the non-fully oxided samples are insoluble in the bead, so of course you don't have the complete analysis or even the bead crack. And also because they are a poison for the platinum Labware. And so it's not, of course, nice to have a destroyed exactly. So the type of product who are insoluble without an oxidation treatment, we speak about sulfides, metal powders, peralloys, carbides, and that's the list of the most used oxidizer. Clearly the most used, and like you explained it already, is the lithium nitrate, because lithium is not analyzed, so it's not contaminating the samples. The problem with lithium nitrate is it's a compound really hygroscopic, and so if you leave it unattended on your bench, it becomes really quickly liquid. And even in the flux, if you leave the pot open, you can have some sort of agglomeration in the flux pot. So it's something you need really to
keep
pay
it
attention.
dry.
Yeah, exactly. And it's why the lithium nitrate is often used, because it's like a sugar and it's very well mixed with the flux. But both are available integrated in the flux, but you need to know that with lithium nitrate you have some I would say things that you need to take care, and the fact you need to dry it. And of course, if it's really complicated, you can mix oxidizer together to improve the oxidation process. So the fusion accessories are there to improve the whole process, and then you can have the disc remover, the glass disc remover. You can have a system to hold the mold and the crucibles, again to protect the surface of the mold. Vortex mixer, I really recommend it to mix the sample with the flux. It's very practical. And then after you have some Teflon system who allow you to clean the mold in the ultrasonic bath without touching the mold surface with a tongs, for example, and destroying again the analytical surface. We have a system to polish the mold, and then we have a system also to store the glass disc for a long time and avoid scratching it together, I would say.
Yeah.
Now some application, we for different type of materials like spine, we can there is flux who are more appropriate, and of course according to the acidic character or basic character, you will prefer, for example, for silica, a flux with more lithium metaborate, and here some example of dilution that are good to use, and we can of course help for that. Here I take the example of the production of cement 40 millimeters bead. We put 1.5 grams of sample with 9 grams of flux 6634 and 0.2% lithium bromide, and in 70 minutes we have the beads cold to cold, so meaning that we put the crucibles cold with the mixture, and then we can collect the beads and the crucibles cold. Another case here, iron ores, again 40 millimeters bead, but here we have a flux containing 5% nitrate. We don't need to do an oxidation step in this case, because the quantity to oxide is not big, and the fusion time is relatively fast, also 70 minutes. And here the case of a more severe or a more complicated product to oxide, and here again we put sodium nitrate in the flux, a little bit more quantity, but we let the machine do 15 minutes oxidation step at 700 to be sure that all the sulfide is oxide in the copper oxide, and that we can go of course to the next fusion cycle. And of course it's a little bit longer, it's 32 minutes in this case. So Paul, I'll let you maybe finish.
Okay, thank you, Frederick. So, well, I think we have seen that fused bead sample preparation really will improve your analytical results drastically, and we have also seen that there is quite a few parameters that may influence good sample preparation, good fused bead sample preparation. But anyway, if you have doubts, you can always ask us, because we, this means XRF Scientific in combination with Alpha One, have the knowledge to help you further. And please understand that XRF Scientific has all the tools that you need to work properly and to make fused beads for any kind of sample that you may have. But it is important, before you start thinking about doing analysis, that you make sure that you select the appropriate tools, and in that way you will be very, very, very successful. So by this, we are just leaving you our contacts. You can note them down, or you will also get the availability of the YouTube film later on. Please contact us always, and whenever you have doubts. And with this, we come to our questions and answers session. Jackie.
Great. Thank you so much, Paul and Frederick. I see there's a question from our attendees. There's one that is asking about how to prepare a blank sample from just the flux, and what do you need to consider and do in order to have a clear disc. So I think he's asking about when sometimes your bead crystallizes. What typically
Yeah, it is strange, but producing a blank with pure flux, we are in pure phase, is sometimes complicated, more complicated than a fusion with a sample. In fact, the trick is to have a very direct cooling after the casting. So it quench the liquid into glass and avoid going to the crystallization. Yeah.
Perfect. And Frederick, tell me, there was an interesting picture there where there was this big hole in the crucible. What do the customers have as options from Labware if they completely destroy their platinum ware, or just in the case where their molds are no longer flat, they are beyond repair in terms of very deep scratches? What can Labware from XRF Scientific do to help them?
Yeah, so of course we are producer of platinum labware, so the metal is never lost. So you can send us back the labware, and then we will melt and produce new materials for you. So I will say, of course, it's a loss because you will need to I will say pay the manufacturing, but the metal is never lost, so you can reprocess it again. And for the molds, when you start to see, so you need to have in the lab a sample you pass every week at least to check that the results are in line with what you expect. And when you start to see that you deviate, then maybe the molds need to be replaced. At least check the molds, and maybe it's time to replace the molds.
Fantastic. And yeah, I think that is all from the questions. But again, if there's any further questions that anyone thinks of later on, please feel free to drop us an email and we will gladly assist and offer you some guidance, especially when it comes to the fused beads. But I think that's it for today. So thank you to Paul and Frederick for sharing your expertise and your practical guidance today. We trust that this has helped demystify the fusion process. And again, as I said, if you have any further questions, please drop an email. And remember, XRF Scientific is here to support you with world-class equipment, consumables, and technical know-how across the globe. And until next time, please join us, and may your beads be flawless and your data rock solid. Thank you all.
Thank you. Bye.
Thanks. Bye-bye.